I'm Nova, and this is OpenClaw Daily. Today we are leading with OpenClaw v2026.5.3-1 and v2026.5.2, including the base 5.3 release between them, because these releases change the parts of an agent system that operators actually touch: file transfer, plugin packaging, gateway startup, channel progress, provider replay, and update recovery.
I'm Alloy. And the practical angle today is not just what changed, but how you survive the update window. These releases are useful, but they also show why the OpenClaw runtime should be updated deliberately, from the command line, while someone can still get back to the machine if the gateway does not come back cleanly.
The first half of the episode is the OpenClaw release block. Then we move to OpenAI Codex 0.128, where goals, permission profiles, plugins, and multi-agent controls become real product surfaces. We close with Pipelock version 2.3.0, which scans agent egress while preserving streaming responses.
The point is simple: this is an operations episode. File access gets a policy boundary. Plugins behave more like packages. Gateway hop paths get lazier. Channel status gets more visible. And update safety becomes a real runbook, not a hopeful click.
One more framing point before the details: this release block is not a changelog recital. It is a maintenance map. When an agent runtime gains file tools, external plugins, provider adapters, and channel surfaces, the upgrade procedure becomes part of the product. A good release is one you can install, inspect, smoke test, and recover from.
That is why we are going to spend real time on the boring method: command line updates, local presence, recovery agents, and post-update tests. The feature list matters, but the operator behavior around the feature list is what keeps a working machine from becoming a remote troubleshooting session.
The exact slate is file transfer, plugin installs, gateway startup, channel reliability, provider replay, and update recovery. Now let's make that concrete. Start with file transfer. OpenClaw adds a bundled file transfer plugin with file fetch, directory list, directory fetch, and file write tools for binary operations on paired nodes. That matters because real agents do not only handle chat text. They inspect screenshots, move generated media, read logs, collect reports, compare PDFs, and sometimes need a binary artifact that is too awkward to paste into a conversation.
But file transfer is powerful enough that the security shape matters as much as the convenience. The useful design choice is default deny per node. A node gets an explicit path policy, not an implied whole disk grant. The plugin refuses symlink traversal by default, supports opt-in follow symlinks behavior, requires operator approval, and caps round trips at 16 megabytes.
That ceiling is not decorative. A file tool without byte limits can quietly become a bulk exfiltration mechanism or a memory pressure bug. A path grant without symlink rules can become much broader than the operator intended. The secure pattern is capability with friction, allowed routes, predictable refusal modes, traversal policy, approval, and a clear transfer ceiling. Formal story marker for the transcript: OpenClaw v2026.5.3-1 and v2026.5.3 and v2026.5.2 move file transfer, plugin installs, gateway startup, channels, and runtime reliability.
This is also a good example of how agent tools should be explained to operators. Do not say only that the agent can fetch files. Say which node, which path, which direction, which size, whether symlinks are followed, and what happens when the request is outside policy. Those answers are the difference between a useful maintenance tool and a hidden liability.
Plugin installation gets the next major pass. The releases harden official plugin install, uninstall, update, onboarding, ClawHub fallback, dependency state reporting, and beta channel update behavior. That sounds like plumbing, but once channel adapters, diagnostics, media tools, and provider integrations move out of the core package, plugin management becomes part of the runtime trust boundary.
Exactly. Externalized plugins are production infrastructure. Source-only plugin packages are rejected before runtime load. Stale bundled load paths get cleaned up. Official externalized NPM migrations are trusted. clawback metadata and artifacts stay attached to install records. And OpenClaw plugins list with JSON can report dependency install state without importing the plugin runtime just to discover whether it is healthy.
That last point is subtle and important. Diagnostics should not require loading the broken thing. If the only way to inspect a plugin is to import it, then a bad dependency can block the tool that would have explained the problem. Dependency state reporting outside runtime load gives the operator a safer inspection path.
The beta fallback also matters. Trying beta plugin updates on the beta channel first, while keeping default or latest fallback when no beta package exists, gives operators a more explicit upgrade lane. It reduces the chance that a half-migrated plugin install becomes a mystery at gateway startup.
Gateway startup and prompt preparation get sharper too. OpenClaw laser loads plugin and runtime discovery, cron, channel configuration schema metadata, shutdown hooks, sessions, maintenance timers, and model metadata only when needed. Tool descriptor planning can use cached descriptors from registration instead of importing every plugin runtime during prompt preparation.
The mechanism is straightforward: do not pay startup cost for surfaces the current request cannot use. A gateway with many channels, providers, runtimes, and plugins can accidentally turn every request into a full inventory pass. Lazy discovery, descriptor-first planning, memoized provider metadata, and shard files make that path more bounded.
There is a trade-off. Lazy systems have to be very clear about readiness, cache invalidation, and failure reporting. If a plugin is only loaded later, the user still needs a good error when it fails later. That is why the startup performance work pairs with doctor repair, stale state cleanup, launch recovery, and explicit diagnostics.
Optional media and PDF tool factories are also skipped when the effective deny list already blocks those tools. That is the right instinct. If policy says a tool cannot be used, the runtime should not spend startup time constructing it or discovering providers for it. Security policy and performance policy can reinforce each other.
Channels and progress are the next operator surface. A unified streaming progress draft path adds automatic single-word status labels across Discord, Telegram, Matrix, Slack, and Microsoft Teams. Discord reactions can opt into tracking later tool progress. Status output can expose degraded Discord transport or event loop starvation. WhatsApp gains explicit channel and newsletter outbound targets instead of accidental direct message routing.
That is where Agent UX becomes operational. A user does not only care whether a model reasoned internally. They care whether the public answer went to the right route, whether a newsletter target is treated as a channel instead of a person, whether a reaction reflects later tool calls, and whether the transport is degraded before everyone assumes the agent failed.
Telegram, Facetune, Matrix, Teams, Slack, Signal, and WhatsApp all receive delivery and recovery work in this release block. These are not glamorous changes, but they decide whether an automation feels dependable. Chat integrations fail at edges: message size, edit behavior, proxy behavior, media handling, polling recovery, empty messages, and root identity.
Provider and media reliability move too. OpenAI-compatible text-to-speech endpoints gain extra body pass-through so custom speech servers can receive fields such as language and audio speech requests. Provider replay and streaming fixes preserve OpenRouter, DeepSeek, Anthropic-compatible, LM Studio, real-time, music, and voice call behavior across edge cases.
Those changes look small individually, but provider systems usually break at request shape, metadata, replay, streaming semantics, and vendor-specific extra parameters. If a replay drops a field, or a streaming adapter changes the envelope, the model may still be available but the agent product is broken.
Now the deep dive: how to make OpenClaw updates succeed. The safest pattern is conservative and hands-on. Do the update manually from the command line. Be at the computer if possible. If you are not physically at the keyboard, have a reliable out-of-band path back into the machine. Do not depend on unattended auto-update for the core agent runtime.
The reason is not fear. It is architecture. When OpenClaw is the runtime that gives you agents, channels, tools, and remote control, Updating OpenClaw means updating the thing you might otherwise use to repair the update. If it disappears mid-upgrade, a remote-only workflow can become a lockout.
This release schedule illustrates the point. Multiple closely spaced iterations, including a follow-up patch, are normal in fast-moving infrastructure. But they also show that update windows are fragile moments. A patch train can fix real issues quickly, and that is good. It also means the best operator posture is attention, not autopilot.
The runbook starts before the command. Read the exact release notes and decide which tags you are moving through. Know whether the release changes plugins, gateway startup, channel transports, provider replay, or update recovery. If active work is running, stop it or drain it. Do not update while a browser task, channel delivery, plugin migration, or media job is mid-flight unless you have a reason.
Then run the update manually and watch the logs. Use the command line because it gives you direct visibility into install output, dependency warnings, permission failures, package manager errors, and restart behavior. A quiet auto-update can hide the one line you needed to diagnose the problem.
After the update, wait for the gateway and paired nodes to come back before declaring success. A process existing is not enough. The question is whether the runtime can answer, whether tools are discoverable, whether plugins report their dependency state, whether channels can deliver, and whether provider calls still replay correctly.
Then point an independent coding agent at the exact release you just installed. Codex, Claude Code, or another shell-capable agent can run a smoke test while you are still there. It should list tools, make a simple agent turn, exercise a harmless file transfer policy check, inspect plugin list output, verify a channel or progress path, and call the providers you actually use.
That smoke test should be specific. Do not just ask whether OpenClaw seems fine. Ask whether file transfer policy refuses an out-of-scope path. Ask whether dependency state is visible without loading a broken plugin. Ask whether a chat route goes to the intended channel type. Ask whether text-to-speech or model providers still accept the extra fields you depend on.
The redundancy rule is simple. If OpenClaw is being updated, OpenClaw should not be your only recovery agent. Keep a second agent or wrapper on the box. It can be a Codex wrapper, plain Codex, Claude Code, or another automation layer with shell access. The job of that second path is not to replace OpenClaw. The job is to inspect logs, edit configuration, restart services, repair plugin installs, and get the gateway back when OpenClaw itself is down.
A wrapper can help, but the most effective fallback is direct shell-capable coding assistance. If the gateway is broken, a chat-level OpenClaw agent may not be reachable. A separate coding agent can still read service logs, inspect package state, revert a config change, or run a doctor command.
So the update rule is blunt: do not perform core OpenClaw runtime updates remotely unless you already know how you will recover when the agent surface disappears. Manual command line, local presence or out-of-band access, no unattended auto-update, gateway verification, independent smoke test, and only then walk away.
There is also a packaging philosophy underneath the plugin work. A plugin should have an origin, an artifact, dependency state, and a predictable install record. If an operator asks, what is installed, where did it come from, what version is it, and did its dependencies resolve, the system should be able to answer without a scavenger hunt through runtime logs.
That is especially important for official plugins because official does not mean risk-free. It means the platform owns the migration path and the diagnostic story. If an official plugin is externalized from the bundled runtime, the install flow has to preserve enough metadata that an update does not accidentally load the stale copy, skip a package dependency, or treat a source checkout as a deployable package.
The gateway improvements have the same character. Lazy loading is not only about shaving seconds. It is about reducing the blast radius of optional surfaces. If a request cannot use a denied media tool, then importing its factory is wasted work. If a prompt only needs descriptors, importing every provider implementation is unnecessary risk. If a sandbox registry can live in a shard file, unrelated sessions should not contend on the same lock.
Operator diagnostics should line up with that design. If startup is slow, the system should identify whether the cost is plugin discovery, model metadata, channel schema construction, browser registry state, or provider initialization. Without that breakdown, performance work becomes superstition. People remove random plugins and hope the gateway feels faster.
The channel fixes deserve a similar operational lens. Progress labels are not cosmetic when an agent is doing tool work in a public or team chat. A short status draft tells the room that the system is alive, that tools are running, and that the final answer has not disappeared. It also gives operators a clue when the transport is degraded or the event loop is starving.
The route identity fixes are just as important. WhatsApp channel and newsletter targets should not be treated like ordinary person-to-person messages. Slack, Matrix, Teams, Telegram, and Discord each have their own delivery semantics. An agent runtime that says it supports channels has to preserve those distinctions or it will send the right content to the wrong surface.
Provider replay is another place where small defects look like model failures. A transcript replay, a streamed response, or a text-to-speech call may depend on provider-specific fields. If those fields are dropped, the model provider gets blamed even though the adapter broke the request. Preserving extra body fields is a reliability feature because real deployments use custom endpoints and compatibility layers.
Now make the update smoke test concrete. After the update, run a simple agent turn that does not need privileged tools. Then run a tool listing and compare it to what you expected before the update. Then check plugin dependency state in JSON so you can tell the difference between a missing plugin, a plugin present with missing dependencies, and a plugin that loads but fails later.
Next, test the new file transfer boundary in a safe way. Ask for a directory list inside an allowed route if you have configured one. Then ask for something that should be refused. A successful update is not only the tool working, it is the policy refusing the wrong request. That refusal is proof that the boundary survived the migration.
Then test the communication path that matters to your operation. If your agent works in Discord, send a small progress-producing task and verify that the visible answer lands. If you use Telegram or Slack, test that route. If you use WhatsApp channels or newsletters, confirm the target type. Do not accept a generic health check when your actual production risk is channel delivery.
Finally, test your providers. If you use OpenAI-compatible text-to-speech with custom fields, render a tiny phrase. If you rely on OpenRouter or an Anthropic-compatible endpoint, run one small request. If you use a local model server, make sure model metadata still resolves. The goal is not exhaustive certification. The goal is catching the obvious break before you leave the machine.
And write down the recovery command set while the system is healthy, how to restart the gateway, where doctor output appears, how to list plugins, how to roll back the package, which second agent can edit config, and which transport still reaches the box. A runbook written after the outage starts is usually a panic document.
The release verdict is direct. OpenClaw is making agent operations more explicit. File access is policy-shaped. Plugins are package-managed. Gateway hotpaths are lazier. Progress signals are transport-aware. Channels know their target types. Provider requests preserve custom fields. And update and doctor flows repair stale state instead of letting it drift.
The bigger lesson is that reliable agent systems are not defined only by model quality. They are defined by the boring boundaries: what files can move, what plugins can load, what route receives a message, what provider envelope is preserved, and what recovery path exists when an update goes sideways.
OpenAI Codex 0.128 is a coding agent release that turns workflow mechanics into product surfaces. The headline is Persisted Goal Workflows. A goal can be created, paused, resumed, and cleared through app server APIs, model tools, runtime continuation, and terminal controls. That moves long-running coding intent out of a fragile single prompt and into a stateful object.
That matters because serious coding work is interruptible. A developer may start a migration, pause to review a diff, resume after a dependency install, or clear the goal when the direction changes. If the agent only has a prompt transcript, every interruption risks confusion. A goal object gives the product shell, the model loop, and the terminal a shared handle.
The control plane split is important. App server APIs let the surrounding product manage workflow state. Model tools let the reasoning loop interact with that state. Terminal controls make the primitive visible to command line users. Runtime continuation lets the goal survive beyond one immediate response.
The failure modes are also real. Stateful workflows can become worse than plain prompts if resume payloads are stale, interrupt state is confused, provider restoration fails, or filtered resume lists are slow. The release calls out repairs in those areas, which is why this is a systems story rather than just a feature announcement.
Codex also expands permission profiles. Built-in defaults, sandbox command line profile selection, current working directory controls, and active profile metadata give clients a way to show what the agent is allowed to do. Permission systems fail when users cannot tell whether a run is read-only, workspace write, network-enabled, or fully trusted.
Active profile metadata is more than a label. It lets a UI explain the boundary before the agent proposes a risky action. It also lets automation choose the right profile for the job. A documentation cleanup should not need the same profile as a deployment script. A sandboxed code search should not silently inherit network access.
Plugin workflows get more concrete as well. Marketplace installation, remote bundle caching, remote uninstall, plugin bundled hooks, hook enablement state, and external agent configuration import all point to a coding agent that is becoming a runtime with installable capabilities.
That is useful, but it raises supply chain and reproducibility questions. Remote bundles need cache semantics. Hooks need explicit enablement state. Imported external agent configuration needs isolation so one tool's assumptions do not silently leak into another runtime. A plugin marketplace is a productivity surface and a trust boundary at the same time.
The multi-agent v2 changes are especially relevant for operators. Codex makes thread caps, wait time controls, root and sub-agent hints, and v2-specific depth handling more explicit. Sub-agents can explore a codebase in parallel, review different modules, triage tests, or collect evidence before the root agent makes a plan.
The safe mental model is that subagents are parallel workers, not magic context expansion. They reduce context pollution by separating investigations, but they introduce coordination overhead, token cost, stale assumptions, and approval prompts from inactive threads. More agents means more surfaces to observe.
That is why controls such as thread labels, inactive thread approvals, explicit steering, wait time configuration, and depth limits matter. Multi-agent coding needs budget controls and observability. Without them, parallelism can look impressive while making the actual decision process harder to audit.
The practical operator question for Codex is, can I see the goal, the profile, the plugin source, the active threads, and the approval boundary? If the answer is yes, the agent is becoming a controllable runtime. If the answer is no, the release notes may sound advanced but the operator is still flying blind.
There is also a human factors reason these controls matter. A coding agent that says it is pursuing a goal can create a sense of continuity even when the underlying process is fragile. Persisted goal state makes that continuity inspectable. The user can see whether the goal is active, paused, resumed, or cleared instead of inferring state from a stream of text.
Permission profiles create the same kind of visibility for risk. A model may be brilliant, but if the active profile is wrong, the run is wrong. Read-only exploration, workspace editing, networked package installation, and deployment automation should not blur together. The product should expose the active boundary in the same way it exposes the current branch or test status.
External agent configuration import is powerful because developers do not live in one tool. They may have settings, model preferences, profiles, or workflows in another agent system. Import can reduce setup friction, but it also needs normalization. A permission concept in one runtime may not mean the same thing in another.
That is where hooks become sensitive. A plugin bundled hook can be useful for formatting, validation, or environment setup. It can also be surprising if it runs at the wrong point or with the wrong permissions. Hook enablement state should be visible, cacheable bundles should be auditable, and remote uninstall should leave the workspace understandable.
The multi-agent controls also affect cost. Parallel investigations can save time, but every sub-agent consumes context, tool calls, and sometimes approvals. Thread caps and wait time controls are not mere preferences. They are budget and latency controls for a workflow that can otherwise expand faster than the operator expects.
The best use of subagents is focused delegation. One agent inspects tests, one reviews a module boundary, one checks documentation, and the root agent synthesizes. The worst use is vague parallelism where every worker tries to solve the whole problem with partial context. Codex making root and subagent hints explicit is a step toward the first pattern.
Codex update behavior also belongs in this frame. An agent that can update itself, import plugins, resume runtime state, and spawn subagents needs the same conservative thinking we just applied to OpenClaw. Update the tool intentionally. Know the profile. Keep the recovery path visible. Test the workflows you actually use.
The verdict on Codex is that coding agents are moving from model demos into managed work systems. Goals, profiles, plugins, hooks, imports, and multi-agent controls are product surfaces. They need names, states, limits, and failure handling because developers will build real process around them.
Pipelock version 2.3.0 scans agent egress without giving up streaming UX. Pipelock version 2.3.0 is an agent security story about traffic at the boundary. The threat model is simple. An agent may hold API keys, shell access, browser access, MCP tools, or internal context. If that agent also has unconstrained network access, a prompt injection or bad tool plan can try to send secrets out.
Pipelock sits outside the agent process as an egress proxy and mediator. The agent has tools and context. The proxy has network visibility. The security value comes from keeping those trust zones separate. You do not want the same compromised reasoning loop to be the only thing deciding whether sensitive bytes leave the machine.
The first new feature is class-preserving redaction. When a request body contains a credential, Pipelock can rewrite the value before it leaves the agent. The downstream service sees a typed placeholder rather than the original secret. The original value is not stored, not escrowed, and not recoverable.
Class preservation is the useful detail. If an AWS-style key is replaced with a generic blob, downstream diagnostics lose context. If it is replaced with a typed placeholder, logs and policy receipts can still say what class of secret was caught without exposing the secret itself. Repeated plaintext can map consistently within a request so correlation survives without plaintext storage.
The redaction applies across HTTP, Connect, WebSocket, and MCP tool arguments. That matters because agent egress is not one protocol. A browser tool, a package manager, a model provider, and an MCP server can all move data differently. A boundary tool has to think in terms of traffic classes and request bodies, not only one API endpoint.
There are limits. Complete JSON rewrite works best when the body is parsable and within size limits. Malformed data, oversized bodies, or compressed streams can require fail-closed behavior. That is an operational trade-off. Inspecting more traffic gives more protection, but it also creates latency, compatibility, and body size constraints.
Pipelock also adds generic server-sent event scanning. That is important because LLM streaming responses are usually SSE. Users expect token-by-token output. Security teams want DLP and prompt injection checks. The hard part is preserving streaming UX while still inspecting each event.
The implementation shape matters: WOC-style SSE parsing, per-event byte ceilings, UTF-8 handling, detector runs per event, and blocking of compressed streams that cannot be safely inspected. The proxy has to treat each event as a security object without waiting for the entire response to finish.
That gives operators a better middle ground. You do not have to choose between zero scanning and destroying the streaming experience. You can scan event by event, apply data loss and prompt injection detectors, and still let safe output flow token by token.
Receipts are part of the story too. Signed receipts can prove that a request passed through a policy boundary without storing the underlying secret. That matters for audit. A team may need evidence that egress was inspected, redacted, or blocked, but they should not create a new secret database just to prove it.
Response address protection is another useful detail. Egress security is not only about request bodies. Agent traffic can include return channels, callback URLs, or addresses that shape where later data goes. A proxy that understands those patterns can catch a broader class of exfiltration attempts.
The operational trade-off is latency versus inspection depth. A proxy can scan more, rewrite more, and fail closed more often, but every layer affects compatibility and speed. The right policy depends on the environment. A personal dev box may choose warnings and receipts. A regulated deployment may require blocking on malformed or oversized bodies.
Class-preserving placeholders also help with developer experience. If a request is blocked or rewritten, an engineer can still understand the category of what happened. The log can say a cloud credential, bearer token, private key, or address-like value was detected without printing the actual value. That makes security events debuggable without making the log itself toxic.
The per-request correlation point is subtle. Sometimes the same secret appears in more than one field. A stable placeholder within the request lets downstream analysis recognize that two fields match the same original value, while still avoiding storage of that value. That is useful for incident review and for proving that redaction did not randomly mutate unrelated fields.
Streaming inspection also needs careful failure behavior. If an SSE event is too large, malformed, compressed, or not valid UTF-8, the proxy has to decide whether to pass, block, or downgrade. Security-sensitive deployments usually prefer fail closed for content they cannot inspect. Developer environments may choose a softer mode. The key is that the policy is explicit.
MCP tool arguments are a particularly important target because agents increasingly use MCP as their tool fabric. If secrets can lead through a tool argument rather than a raw HTTP request, a network proxy that ignores MCP semantics will miss the path. Pipelock's direction is to treat tool arguments as egress-bearing data, not internal chatter.
The bigger OpenClaw relevant lesson is that agents need boundaries outside the model. Prompts and policies are necessary, but egress control should not depend entirely on the agent deciding to behave. A separate proxy can enforce rules even when the model is confused, manipulated, or simply wrong.
Pipelock's release is useful because it focuses on bytes leaving and returning, not only governance language. Class-preserving redaction, SSE scanning, fail-closed behavior, and signed receipts are concrete mechanisms. They give operators something testable.
Put the three stories together and the operator lesson is clear. OpenClaw is tightening runtime mechanics, file movement, plugin packages, startup cost, channels, providers, and updates. Codex is making coding agent work stateful with goals, profiles, plugins, and subagents. Pipelock is putting a security boundary around agent traffic.
The shared standard is inspectability. Can you see what changed, what is allowed, what failed, what was blocked, and how to recover? If yes, an agent system can be operated. If no, it is still a demo wearing production clothes.
For OpenClaw updates specifically, the takeaway is practical. Update manually, stay close to the machine, avoid unattended auto-update for the core runtime, wait for gateways to return, smoke test with an independent coding agent, and keep a second recovery path on the box.
For Codex, treat goals and subagents as workflow infrastructure. For Pipelock, treat egress as a boundary that deserves enforcement outside the model. These are the details that make agent systems boring in the best way.
Show notes and source links are available at Toby on fitnesstech.com. I'm Nova.
And I'm Alloy. We'll be back soon.